Hello, ladies and gentlemen. So today we will introduce our work on robust multiple instance learning with cascaded Dirichlet process. So first, we are focusing on the multiple instance learning problem, which is given a bag of instances. For example, particularly we try to tackle the most difficult problem in multiple instance learning, which is the whole site image analysis, that we treat patches as instances, and we have the corresponding back labels. The aim of this task is to aim to train a model that's to predict the back level labels, for example, labels of whole slides, where the model is supervised only or mostly by the back labels. We assume that the supervision on the instance level is very weak. And there are several challenges. So the first one is 16 aggregation methods based on the first order distance. So if we look at the figure at the right, you can find that we are clustering the instances into latent clusters, then we are making prediction from these latent clusters. And when we're doing clustering, then which is aggregations, we mainly focus on the mean difference, with like the k-means, like the mean difference between the centroids, but we rarely consider the covariant structures of each clusters, which is the distributional characteristic, which make the resulting clustering accuracy is low and hence hinder the downstream task performance. And due to the weak supervision of multiple instance learning, the predictive model are easily prone to overfitting and have tested performance, which is the most common challenging problem in multiple instance learning. And thirdly, we consider uncertainty estimations. We find that the most of the current methods are deterministic, which fail to capture or address the model-wise or epistemic uncertainty, which make their capability in predicting uncertainty relatively low. So in light of the above problems, we are going to propose a cascaded Dirichlet process. That is, we majorly working around the Dirichlet process model, which is we partition the sample size into several partitions, and then we assign a Dirichlet process, Dirichlet distributions on each of the or the probability that each of the partition can be selected during training. And each of the partition we assign different probability measure. Basically, it is applicable on a mixture model. And then we apply this Dirichlet process on aggregation first. We use Dirichlet process to cluster the samples into each of these partitions. And then we perform predictions with the Dirichlet process again. So next, here's our overview of the framework. So as usual, like in the standard whole site image analysis, we encode the image patches into embeddings with a key-magnet encoder, which is quite common in almost all multiple instance learning. And then we use the Dirichlet process to cluster the instances into latent clusters or central with respect to centroids and all the covariant structure. We can find that each cluster has their unique distributions, parameterized distribution family. And then we apply the Dirichlet process again to make predictions on whether this slide is normal or tumor. That's we collect evidence into respective clusters. For example, in cancer predictions, we have the normal cluster and also the tumor cluster. Then the posterior probability can be made from this probability, can be treated as the logic from this probabilistic model. And then we have two tasks, for example, the localization task and also the detections and generalization task, basically to measure its capability estimating the uncertainty. So here we perform two tasks. For example, we perform classification and also subtyping. In addition, we also perform OOD generalization, OOD detections. So we can observe that for subtyping and classification, we consistently outperform the baselines, and particularly the recent graph-based model and another probabilistic model, which is Bayes-MIL proposed recently using a log normal mixtures model on each instance. And also we perform qualitative analysis. We can find that throughout the samples, and our model can outline the tumor region better than the existing methods. And also we perform ablation analysis on the concentration rates and also performance with different pooling methods and also maximum mixture components that our methods also generate reports. So to summarize, we propose a cascaded Dirichlet process design, which is a novel Bayesian non-parametric framework to multiple instance learning. And then By enabling the data distribution to stochastic, our model captures the uncertainty for more trustworthy predictions. And we have extensive experiments, so feel free to scan to see our repos for more details. Thank you very much.